www.nanohub.org. You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
Okay, so this is lecture 22 and non-ideal effects. And in this, by this non-ideal effect, I mean there are some additional complexity that we want to look into for the IV characteristics. The first one is junction recombination, because we haven't been sort of putting the recombination away, but you know, you cannot do it forever. And we'll talk a little bit of impact ionization before concluding. We are still talking about the DC characteristics of a diode and at various bias conditions. And today we are going to talk about this region 6. This is trap-assisted recombination generation. So it's almost, it happens only at a very low bias. That is where you can see it. It happens at high bias also, but I'll show you in a second why you will not see that effect in a high bias case. I'll show you in a second. And then we'll talk about this other aspect of it. Now it's a little bit mathematically complex. I cannot explain every step. I can explain every step, but I shouldn't go through them all. You should be able to follow the math once you go home and trace through the argument. One argument we had been making that if you have the device in equilibrium, the Fermi level is flat, there is a built-in potential of Q VBI, and the carrier concentration has a certain profile as shown here on the right-hand side. You can see the blue remains a majority carrier on the left-hand side, becomes a minority carrier on the right-hand side, and falls off in between. Similarly, the red, large on the right-hand side, very small on the left-hand side, and falls in between. But the idea is that in equilibrium, if you take any 2 points at a given location, multiply them, what is that value? So always equal to Ni squared. So therefore, there is no recombination generation because the numerator of the recombination generation is Np minus Ns squared. In equilibrium, no net generation or recombination. However, as soon as you apply a forward bias, let's say by the amount of V, then the carrier concentration will not remain equal to Ni squared anymore, right? So that is what I have shown on the bottom right figure, that the carrier concentration is no longer the same. And in the junction region especially, it has been modified quite a bit. You can see the linearly drooping region on the blue curve. That's the diffusion. Remember the triangular region? So that's why I'm trying to show it there. But now I want to just focus on the junction, because junction is where recombination generation plays an important role. Now, why in the junction? It's because when you diffuse a dopant in a, let's say, in a p-type material, you diffuse the dopant in the junction region, many times they do not find their chair, meaning they did not find the spot they should sit in. And therefore, junction is always prone to a lot of defects, and right processing is very important. So you primarily focus on the junction region where recombination generation might play an important role. So let's try to work it out. I just want to calculate the current due to recombination alone, assuming I have calculated all other currents previously. Now what happens that the electron and hole comes in, and you can see that the red and the blue, they will come and they can come halfway in the junction and they can recombine, right? Why don't they recombine on the right hand and the left hand side? Because on the right hand, left hand side, carrier concentrations are close to equilibrium. I'll show here that this is a huge amount of carrier concentration in the junction, and that causes a significant recombination. This expression, you know, and fear, and this is a complicated expression, but this is, what expression is this? This is Shockley-Reed-Hall expression, right? But this time I have written it as a function of Nx and Px because carrier concentrations are not constant everywhere. You have solved this problem also in your homework. Now let's try to calculate this nx and px, and we'll insert it in and see what happens. Now, if I assume tau n is equal to tau p, for a particular case, it simply means that their velocities are approximately the same. Okay, EI is equal to ET, that all the traps are mid-gaps, sort of, so that N1 and P1, you know this, right, becomes equal to Ni. Okay, it simplifies my life, doesn't change the physics. So I have a very simple expression where Np is given by Ni squared, an exponential of the voltage, and then in the denominator, tau have been taken out, N and P together, and N1 and P1 has been written as 2Ni. Okay, this is no rocket science here. Hopefully you remember the homework. Now this is, I have mentioned this already, that in non-equilibrium case, the splitting of the quasi-Fermi level at low current levels, right? Otherwise, there will be droop in the Fermi level, and in the junction, the separation will have a delta Fn and delta F sub p. That I am not writing, low current level. So the carrier concentration goes like this. But first, let me convince you that the carrier concentration will be given by this red line. Do you agree? Ni exponential of Fn minus Ei. That you agree, right? That's the traditional expression. Now Fn at low current is flat up to the other side of the junction. So I shouldn't really have to touch Fn. So I keep it the same. But Ei, well, as the junction, as the potential is varying, Ei should follow along. So Ei will have a reference Ei sub L, which is whatever the I is on the left-hand contact, and the potential. Whatever potential does, Ei does the same thing. So you put it in there. And that's the second expression. So only x dependence is coming through the potential Vx. Okay, so what about Px? Do you agree? Because N and P is equal to Ni squared to the exponential. That's on the numerator. On the denominator, I have simply written an expression, borrowed the expression for N sub x, and just put it in on the right-hand side denominator. And if you divide, you can see that Ni squared and Ni will take care of one Ni here. This is a constant that comes here, and the whole thing gets flipped, so you have a minus sign. But other than that, I haven't done anything here. Let's see. Okay, now let's see. So we'll redefine this term. I'll go through the next two things because it's difficult to explain in a board like this, all the steps, but I'm just renormalizing things and calling variables various names so that I can write it a little simply, don't have to carry around all the KTs and all other things, and I can emphasize on the shape of the function. Now, do you see on the denominator why it will become a cosine hyperbolic? Do you see that? What is the expression for cosine hyperbolic? E to the power x plus e to the power minus x divided by 2, right? So you can see why there should be a cosine hyperbolic. Do you see why there should be a sine hyperbolic? Because if you pull out e exponential of ua over 2, pull it out, then the remaining piece will become a sine hyperbolic because it has a exponential to exponential subtracted. Now the applied voltage is a constant. It doesn't depend on a position. So I should be able to pull it out of the integral. That's what I have done. And only place where the x dependence remains is in u, right? U is the new v here, normalized v. So that is the only place it remains. And then if I want to integrate this out, I have just written that. If I want to integrate it out, I just provided the two steps that is behind that step I just made, that why there's an exponential of cosine and there's a sine hyperbolic in here. This is just, go back, do in your room for a few minutes. That should be simple. So once you have that, you can integrate this, and that requires the integration table, and I will not do that. But only point I will point out is that u at x at a given point, generally one can find out from this triangular electric field what the potential is at various points. But in general, that's difficult. So I will replace it with a constant electric field and call that E max. And then E max multiplied by x is what that U is. This is an approximation. But now I can do the integration. And that's it. That's the integration. And this one has two features that I want to emphasize. One is the effective width. Do you agree? KT over Q, what is that? That's the dimension of a voltage. If you divide with E max, which is the electric field, what do you get? You get a dimension of a space or distance. So that is of sort of the effective distance over which recombination is occurring. The right-hand side, do you agree that that's essentially the extra carrier concentration that you have in the junction region, exponential of QVA over KT. Now, why is that 2? Because it's middle of the junction. Because the whole thing is separated by VA, in the middle of the junction is separated by VA over 2. So therefore, you have that. And this feature, that it goes half of the slope of the classical diffusion, that is an indicator that you have a huge amount of traps in your system. You better take care of it. Otherwise, your diode is not going anywhere. That signature of that 2 in the low current part. In the high current part, what is the signature of? That is the ambipolar part, right? Ambipolar has lots of electrons and holes together. That's where the 2 comes from. That's high current. But at low current, if you see also you have half the slope, then you know that that's because there's a lot of traps in your system. And where is the trap hiding, by the way? Do you see where the trap is? In the tau, right? Because tau is inversely proportional to the number of traps. If you have a huge amount of traps, then they recombine very quickly, tau is small. If you have no traps, tau is infinity, no recombination current. So that makes sense. And this is a very important problem, by the way, because we had been thinking about just one-dimensional cut. Most of the time, it doesn't look too bad. But you see, the problem is that many times, most of the time, diodes are two-dimensional. You cover it up with the oxide so that dart doesn't go through from the top. It doesn't go through. The junction is protected. But do you realize that anytime you have a curvature on the corners, the electric field will be concentrated on the curvatures, right? Do you know that? That generally if you have a sphere, then you have a certain electric field. But the lightning rod on many of the top of the homes has a very asymmetrical shape, right? It's very long and very sharp because sharp points have high electric field. So what's going to happen that although you did your design on one-dimensional thing that I just showed you in the previous one, in the real device, you will have these corners where the electric field will be very high. And in that case, you can have a significant amount of recombination on those points. So one has to be very careful about designing junctions for practical devices. Now that was all about forward bias side. That's fine. On the reverse bias side, the answer is very simple, fortunately, because in the reverse bias side, again, you have done it in homework. Have you? In the reverse bias side, you do not have any carriers. N and P are both 0. And so therefore, the generation current is Ni divided by tau. You have done this in last homework. So you can integrate it out. Now this time, even I can do this integration, because Ni divided by tau, that's a constant. So I can pull it out. I'll have a W. And what is that W saying and telling us? This is the width of the depletion. Do you remember that the depletion width, as you apply reverse bias, that becomes larger and larger and goes as square root of the voltage, right? Applied voltage. VA has a negative sign here. So that overall thing is positive. And so therefore, this current in region 4 increases with the square root of voltage. And that's why this current keeps increasing. Otherwise, ideally, it should have been flat. The diffusion current should have been flat. Because of the recombination generation, generation in the depletion region, you will have a square root dependency on the voltage. Again, that's another signature to know that you have too much defects. Okay, I will start doing this non-ideal effect associated with impact ionization a little bit. Let me just show you one slide and then we'll continue. So the final point I want us to discuss is this breakdown due to impact ionization, and this is how it occurs. Now you are in reverse bias. Right hand side is grounded. Left hand side you have applied a huge positive bias, right? Positive on an N side is a bad thing, means it's in reverse bias. What happens that think about an electron coming from the top side. It's like one skier is sort of standing on the top of a mountain. Now that electron comes in, if it is not scattered by the phonons, which is lattice vibration, then it can have a certain amount of energy, right? If it has enough energy larger than the band gap, then, and in fact it turns out 3/2 band gap. Yeah, it's a 50% more than the band gap. If it can somehow gain that amount of energy, then it can kick away, it can scatter with an electron from the valence band and kick that electron up in the conduction band. Right? Now it has 2 electrons, 1 hole. These 2 electrons keep going. It's like a second skier has joined. 2 electrons starts going. Let's say phonons doesn't steal its energy. It gets 3/2 kT, 3/2 the band gap, approximately. Then this 2 scatters with 2 more electrons from the valence band, gets its friends up in the conduction band. Now I have 4 electrons going. And how many holes? I had 1 from before. This time I have generated 2. I have 3 electrons, 3 holes going. And you can very quickly see that 1 to 2, 2 to 4, 4 to 8, 8 to 16. What is this progression? This is an exponential progression, geometric progression. So therefore, eventually an exponential progression, and therefore huge amount of current will start flowing through such a system. And this is called an impact ionization. And impact ionization is also maybe called as a inverse OJ process, because OJ forces them to combine and go down. Here, electrons are being generated. Why doesn't it happen when the bias is low? Well, if the bias is low, no matter how much bias you put in or how much what you do, it never has enough energy larger than the band gap. And if it doesn't have any larger than the band gap, no hope of impact ionization. So therefore, in the forward bias case, right, or in the small reverse bias case, impact ionization doesn't occur. And so this is it keeps going down like this. Somebody help me to do this animation. Let's see how it works. Not too bad, what do you say? So, but you get the idea, right? How many electrons and how it will rapidly multiply. Now, the math part of it, I will take up in the next slide. Okay? All right. So, what you just saw in the previous slide was this idea that if you have an electron from the top of the conduction band, shown here in single red circle, then when it gains enough energy from the electric field, this is a reverse bias PN junction, you remember, then it is going to gain enough energy larger than the band gap, and most of the time almost 50% larger than the band gap. In that case, if it can survive that far without scattering, then it is going to excite an electron from the valence band, which is shown here in blue. It will leave behind a hole, and correspondingly an electron will go up, and then there are 2 electrons. And in this process, 1 electron generates 2 electrons, 2 electrons generates 4, 4 to 8, and this process continues like an avalanche. And the same thing is going to happen for the holes, because if you consider the holes that have been generated in this process, when the world is upside down for the holes. And so holes would like to go from left to right, and this electric field assists them. And when in a high electric field it has enough energy, the holes can scatter and it can generate among themselves, and it can also pump an electron up to the conduction band. So both this avalanche goes out and goes down, in parallel, and as a result there is a huge flux of electrons flowing through. So let's see how, if you take a small chunk between 0 and W, a small grid, delta X, let's say 100, you divide it and you take one small chunk. In that case, if you look at the electron number, then I will say that the electron number at X plus delta X out of that little box is whatever electron came in, INX, and then the electron multiplied by its impact ionization probability, because not all electrons had energy or were able to gain energy equal to the band gap or more than the band gap. Only a fraction did, and that fraction is, let's say, alpha n, that were able to ionize the electrons and therefore put them in the conduction band. So this impact ionization would be alpha n multiplied by In. That's the contribution from the electron side, but the holes are also doing their own multiplication, and every time a new hole is generated, a new electron is generated as well. As a result, the term in blue, that is the whole contribution to this impact ionization process. Remember, all this top line is all electrons actually. This is just contribution from various places. Now, one thing I would like you to notice is the x-axis I have drawn here is in a typical from right to left, so that the signs will remain consistent. Okay, so this is a very simple equation that we know how to solve, because if I just bring the right hand INX to the left hand side, divide throughout by delta X, then you realize that this becomes a simple first order differential equation of how the electron current grows as a function of distance, right? Because of the impact ionization. And you can see this equation you may have seen before. If there were no impact ionization, in that case, alpha n and alpha p is 0. And you see what this equation is? This is simply divergence of J is equal to 0. So this right hand side is like a generation term. Do you see? Previously you have seen divergence of J is equal to generation minus recombination. So this whole thing that I'm showing you here is actually nothing new. It's just the generation term. But this time we can solve it. So for example, the electron current, remember this is steady state. There is no derivative term for time. In steady state, the current must be continuous. That whether you look at in the right hand side, in the middle, or in the left hand side, the total current, sum of the electron and hole current, that must be continuous. And that total current, if I call that total current I sub t, whatever that current is, I don't know yet. If I call that current I sub t, I shouldn't carry around a x around it, because it is independent of position. And the whole current, since the current must be conserved, must be written as It minus I sub n. Now this is only in steady state, of course. If you are doing a transient problem, you cannot write it this way, because then it will be depending on both time and position. Okay, so if you have this, then you realize that immediately this becomes a differential equation with the only unknown is In, and It, whatever it is that one can calculate in magenta, that will become, that's a constant. Now this is a first order differential equation that you have solved many times in your life. You may not recognize it here. So people use it something called an integrating factor. Do you remember first order differential equation of this sort that has both the first derivative and a linear term? So if you do not remember, just open up a book or search it in Google called integrating factor, and you will immediately see that the answer you get looks something horrendous like this. But it's not too bad, because as electrical engineers, we'll actually begin to throw away most of the terms and only keep the one that are most interesting. But the thing is that you can sort of see why the solution has to be like this, right? You can see there are lots of exponentials floating around. And when you have exponentials floating around, that's sort of saying that if you put a small amount of current on the one side, that is going to multiply geometrically, 1, 2, 4, 8, and eventually when it goes out from W, by the time it goes out to the W, a huge amount of current will go out. So therefore, there are lots of exponentials floating around. And you can also see IN of 0. IN of 0 is the amount of injected current on the right-hand side of the junction. Where is that current coming from? Do you remember that in reverse bias, in the minority carrier side, one side of the carrier concentration was suppressed to 0, right, in the reverse side. As a result, there was a diffusion flux, a constant diffusion flux coming out from the right-hand side. So that minuscule amount of current, that will be the seed of this avalanche, and then it will proceed. So that's the right-hand side, the one at red. IN0 is the diffusion, reverse diffusion current flowing through the diode, right? And this is something we have already calculated in our previous class. And then, of course, INW is the total amount that is getting out from the left-hand side after all this avalanche multiplication. Immediately you realize IN is very small, IW is huge, right? Because of all this impact ionization process going on. Okay, and alpha and alpha P, you remember, these are, what are these? These are impact ionization coefficients. How many electrons does one electron generate as a result of impact ionization per unit length? So this number can be 1000 electrons, new electrons generated per injected electron per centimeter to a million. That means, so you can see it's a very efficient process at high voltages. This I have already told you, that the hole current and the electron current is constant at any point. And if it's constant at any point, obviously it's constant at W. So I am writing it I sub T. Now look at what I did next. What I said that I can drop IP of W, right? The whole current at beginning of W. Is this correct? This may be correct because you see current is constant and the electron current has grown huge amount by the time it has reached W after all this impact ionization. If the current has to be constant and this one component has grown exponentially, the other piece must be negligible, right? So therefore, I drop that term which is IP at W. Of course, I couldn't drop IP at 0 because IP at 0 is a huge number. So therefore, you have to be careful how you drop it. And also, let me write this quantity that IN of 0 as a fraction of IT is some number I sub P. That could be a million. So that is the total current that is getting out at the point W relative to the current that was injected on the initial seed point. That's really, I am calling a global multiplication factor, M sub P. So this number, by the time it is done, it could be, you may inject one electron and you can get 10,000 out from the W point. So that's what this number is, a very large number. Okay. So if I have these two relationships, then do you see I can simplify it in this way? Do you see this? On the right hand, look at the first equation on the top side. IN0, I'm dropping it. That's small. Do you see the magenta, the one shown in magenta? That I'm cross multiplying. And IN at W and IT, is that equal to 1? Almost equal to 1. Do you see that? Why? Because most of the current which is getting out at W is the electron current. I do not have any hole current. So therefore, IN at W divided by IT is very close to 1. So I have 1. I cross multiply the whole thing and just exchange sides. And that will give me this very simple relationship. Of course, it's not simple enough for me. I need to simplify further. So let's see what we do. But do you see what term, next term you should drop? 1 over MP. This M sub P is 10,000, let's say. So compared to 1, well, that can go also. So if that can go, 1 over MP, then I'm carrying around just a 1. And if I'm carrying around just 1, then it's already simple enough, but not really. Now I'm going to further assume that the number of electrons, extra electrons generated by an electron and number of extra electrons generated by a hole, they are the same. Now, of course, they cannot be the same, right? Because electrons can gain energy, they have a different effective mass, so they can gain energy a little bit faster, let's say, than the holes. Holes are heavy and sluggish. They don't get energy from the field as easily, and phonons can steal its energy very easily. So in general, if you look at your book, reference books and other things, you will see that alpha n and alpha p are not the same. But, for the time being, let me assume they are the same. If you want, you can put the right values in and you can do the integral. But if I set alpha n and alpha p equal to each other, then what should be the fate of the exponential? Well, that will be gone because that's e to the power 0. Now that's getting simple enough. Further, I'm going to assume that alpha doesn't really depend on position. Because if the electric field is constant in this starting from 0 to W, if it's so constant, then I can say alpha is a constant. But of course, it's not a constant. You can see the electric field shown here in the bottom is like a triangle, right? It's not a constant. But what is going to happen that I'm going to show you a little bit later, that most of the impact ionization occurs at the maximum electric field point. So actually, we are talking about a very small region close to the peak of that triangle. And so I will be taking alpha p out of the integral as well. Now that's simple enough for me. Because if I take alpha p out, if I set the exponential top of that 0, then I have nothing left. I have alpha p multiplied by W equals 1. And this is when, this happens when significant avalanching is going on. Because without significant avalanching, 1 over mp, that I couldn't neglect compared to 1, right? So this condition only happens when I have a significant avalanche current flowing, then I will have this. Now this alpha p, what is this? Alpha p is number of extra electrons generated per injected electron. And it depends on the electric field, because the more electric field you have, it is easier for the electrons to gain energy, right? As a result, this has typically, if you look at the experimental data, people have done a lot of beautiful theory. Many famous professors have spent probably a significant part of their life looking into this type of impact ionization process, especially in the 60s and 70s. And one simple form that sort of looks correct in terms of electric field is this. Now, do you realize why this equation might be right? You see, if the electric field is very small, then the exponent is very large, and e to the power a very large quantity is 0. So you don't have much impact ionization when the field is small. But if the field is very large, then you can see that gradually the magnitude of this quantity will keep rising. And as a result, you will have a huge amount of impact ionization if the electric field is high. Okay. Now, if that is the case, what electric field should I put in? Well, if I solve the diode equation correctly, then you can see the blue and the red triangles depending on various reverse biases. I can always calculate that. Do you remember? Depletion approximation, the charges, and the triangles that we created. So I can always create that. And I realize that the maximum electric field will be essentially, I can put the E max in place of E, the electric field E, and calculate alpha. Now, or on the other way, if I know W, the depletion width, then the point where avalanche will begin is given by 1 over alpha, but that electric field, from that I can also calculate the electric field. A naught is known. A naught and B are known material parameters. So only unknown in that case is the electric field E, and from that I can calculate the voltage, right? If I know the electric field, I also know the voltage. Voltage at which this diode will break down by avalanche, right? By just using this relationship. Do you see this? Electric field, as I have already told you, that this is a formula that we have derived already, right? Do you remember that VBI minus VA and its reverse bias? So this should be a plus sign, VBI plus magnitude of VA. And then from this, if we insert back in the equation for alpha P and require that condition, alpha P multiplied by W, that be satisfied, only thing unknown in that equation is the applied voltage. And as a result, I can immediately tell you at what point is this diode going to break down by avalanche multiplication. Now, this is a very important problem. Of course, in technology, there's a very important problem. There are places where this effect is actually used in great advantage, and sometimes it is bad. There's always good and bad. On the top side, where I say good, these could be imagers, where you reverse bias a diode just before impact ionization point. So it hasn't really impact ionizing a lot. Now a single photon comes in. That's the seed. The single photon comes in, generate an electron-hole pair. And now you have an electron which is falling down this huge potential, and similarly a hole falling down the potential well, or not potential well. It's a from the mountain, top of a mountain going down sort of, down the hill. And in that case, you can have a single photon detectors based on this avalanche process. But sometimes it's bad. For example, there are places where you do not want impact ionization. And the corners, I have already mentioned, the corners have very high electric field, like a lightning rod. And in that case, let's say you have done a one-dimensional analysis, everything is fine. You put your diode in the product, all of a sudden you see it's breaking down all the time and your diodes are burning, right? Customers are returning your product. That is because you haven't designed the junction properly. Junction electric field was too much. So when you're applying a reverse bias, this is breaking down from the corner, and avalanche is occurring from the corner. And then the diode cannot function. So depending on the application, different things might happen. How would you avoid that? This is a very nice trick how you can avoid this type of problem. And the trick is this. Instead of having an abrupt junction between N and P, all you need to do is to insert a little I region. Little I region in between. So put a little bit lighter dope region. Now I'll see whether you understood the previous concepts now. Do you agree that the electric field on the left-hand side for the abrupt junction is a triangle, but that of a region which has an I in between is really like a trapezoid? Why is it? Because by the time you come to the intrinsic region, whatever electric field you came with, that electric field must continue, right? Because there is no charges to capture the field. So that is the base of the trapezoid. And of course, once you come to the other side, the electric field is going to go down and go to the zero value, because it must start at zero and end at zero. Now, do you remember I have applied a given bias across this? If I have applied a given external bias, then the area under these two triangles and two curves must be the same, because voltage is simply area under the integral of the electric field. And electric field means the area under the two curves must be the same. Now, if the area under the two curves is the same, which one would have higher electric field, do you think? Obviously, the abrupt junction, because this one will have significantly lower electric field. So therefore, just by inserting a thin insulating or intrinsic region in between the abrupt junction, you can lower the electric field significantly. And in fact, this is what you will hear the term as we go on, the term called lightly doped drain. This was a huge problem in 1980s for MOSFET design, because MOSFETs were failing by hot electron injection, and one person essentially came up with the idea that you just put a lightly doped region in between the heavily doped region. I will come back to this point again. But the point is that actually allowed the scaling, MOSFET scaling in your computer, that to continue for many years in 1980s, just based on the concept that I just showed you. So none of them are just, just to torture you. These have actual and practical relevance. So this is the point I wanted to make, that if you insert an intrinsic region, that can be excellent. Now, one thing I must explain to you, that this analysis that I showed you, this dates back to 1960s, when the diodes were really big, the junctions were huge, and doping was one side 10 to the power 16, another side 10 to the power 17, this centimeter cube, this type of doping, low doping. These days, however, in modern MOSFETs, in many junctions, the doping on one side could be 10 to the power 20, and another side it could be 10 to the power 18, huge doping. If you have huge doping, the junction is going to be very tiny, right? Very small. As a result, when the electron comes in from one side, it may be able to go from one side to the other side without ever scattering. That's ballistic transport. If you don't scatter, of course, you cannot really do any impact ionization, right? You need to scatter with other electrons. So in case of ballistic transport in a highly doped junction, everything that I told you might not be correct. In this case, an electron, and that's called a dead space, the space you need before an electron can impact ionize. You know, the first one it has to start. Now, if it is a huge junction, you can impact ionize many times. You can start with 1, get out with 10,000. If, on the other hand, it is extremely small, let's say in the tens of nanometer, in that case, electron can get out without impact ionizing. So you shouldn't, anytime you see this situation, you shouldn't immediately try to apply the classical formula. You should see whether it is relevant or not. Now, one final thing is, how do you differentiate between Zener tunneling and impact ionization? Do you remember? Both in the reverse side gives huge current. One by tunneling, another by impact ionization. Now, generally, one rule of thumb, which is not a very good way of differentiating, is that Zener tunneling always occurs at a much lower voltage compared to impact ionization. I'll ask you to verify this statement. This is an interesting statement that Zener tunneling would occur about 1 volt. Generally, impact ionization occurs much later. You should convince yourself why this should be the case. But more importantly, you see, the interesting thing is, Zener tunneling is a tunneling process. Electrons slowly going to the other side and it doesn't have too much noise. If you see, it's a regular pattern of electrons sort of swimming through the band gap region and getting to the other side. Very calm current, right? Very quiet current. On the other hand, impact ionization is a horrendous thing going on. You know, electrons, holes are being generated. So on the output side, even if you have the same amount of current, you will see impact ionization has significantly more noise. And as a result, that tells you that this is impact ionization versus Zener tunneling. And also, impact ionization is a highly temperature sensitive function, remember? Because phonons are taking away its energy, band gap is changing because of this temperature. On the other hand, Zener tunneling is much less temperature sensitive. So by looking at this, you know, you have to find out why it's breaking down before you prescribe a fix to this problem. And this is what you should be looking for, the signatures like a doctor, you should be looking for before you prescribe a medicine for the patient. So that's it. I explained the region 5 and 2 physics of region 5 in terms of Zener tunneling, or it could be impact ionization, whichever occurs first. So we have actually gone through all these DC characteristics. Region 1, purely diffusion. Region 2, what is that? Half the slope, ambipolar transport, because electron and hole were so much, they essentially become equal to each other. So the Ni squared divided by Na, it picked up a square root. Similarly, region 3, what is it? Huge injection, so that there was a huge resistance drop in the bulk region itself, delta Pn and delta P. Region 4, what is this? This is generation, square root of the voltage as the depletion width is getting up, then the thermal generation process increasing with a square root of delta V, applied voltage. Region 5, either Zener tunneling or impact ionization, and you know the physics, how to calculate them. 6 and 7, well, 6 is trap assisted recombination in the forward side. And again, just like number 2, 6 has half the slope of the diffusion regime, because electron and hole must be equal to each other before they recombine. So if you see a half slope region in early low voltage, then you know your junction is horrible. There's lots of traps sitting there, you'll have to fix it, right? And 7, well, 7 was again a tunneling process, and that's the ECE606 tunneling. You remember that how under heavy doping condition, electrons can flow from the conduction band to the valence band of the other side, the extra current component. Wouldn't happen in low dope samples. Okay, so I just try to describe the physics of various pieces, and junction recombination is very important. That's a process maturity tool that one can use it as a process maturity tool to see how many defects you have. If you have very low, this region 6 that you have, sorry, very high region 6 in low voltage regime, you better go back and fix your process. Otherwise, this product isn't going out of the door. Now, as I said, impact ionization is very important, and wide variety of devices use this. And these are commercial products that you can buy in various places. Go to Radio Shack, you may be able to find some of this. And now let's move on to AC response. We are done with DC. DC is gone. Let's talk about AC now. AC is, I'll apply a small bias and small signal and see how it proceeds, how the same thing proceeds. Okay.